In this lesson, we're starting topic 15. In this block, we are going to be looking at solving for unknown triangle sides using what are called special right triangles. Now, we are going to skip question 1 in your notes, which is just a review question, so that we can focus on what our lesson is on today. So if you'll remember, we have been revisiting the same problem several times throughout this year about finding the distance across a pond, but we're not doing so by swimming across it. We're doing it by using what's called indirect measurement. So number 2 on your notes says, what does the term indirect measurement refer to? Remember, that's simply finding a distance without actually measuring it. So if I wanted to find the height of the flagpole in the front of the school, I would probably use an indirect measurement. I wouldn't want to actually climb the pole to measure it. So we have found the distance across the pond using congruent triangles. We've used similar triangles. And so now we're going to be looking at a new way. We're also going to get an introduction into trigonometric ratios this topic, and that relies heavily on similar triangles, which we have learned about. Trigonometric ratios are simply ratios of two sides of a right triangle. So we are only going to be applying trig to right triangles, even though we have non-right triangle trig as well. We hope to get to that at the end of the year, but we'll see if we have time. Now, just as a reminder, remember anytime you write a ratio, you're going to be writing it as a fraction, and that fraction must be simplified. So even though you can write ratios with a colon and using the word to, T-O, we are going to always represent them as fractions and always as a simplified fraction. So you would never give me a ratio of 4/8. You would simplify that to 1/2. So in the problem of the park ranger trying to find the distance across the pond, we've used congruent and similar triangles like I said, but in this case there's physical obstacles that are getting in the way of the measurements needed. And so the ranger's aware that the sides of a right triangle have special relationships based on the Pythagorean Theorem, but knows that right triangles also have relationships between the sides and angles that can help her find the unknown distances. So we're going to look at this animation to see if that will help us here. So here is the problem, finding the distance across the pond. And so I want you to see that the first thing that the surveyor is doing is standing here at point B as the other person is walking perpendicular to the distance across the pond, so that we maintain a right angle here at vertex B. And so the other person with the transit is walking out here and checking the angle, and then walking out and checking the angle. And that person keeps going out until they reach an angle of 45 degrees. And so it's a special angle because that creates a special relationship. So if the park ranger can keep checking until they create a 45-degree angle, knowing this is a 90-degree angle allows her to know that this other angle is 45 degrees. Now, how does that help me know the distance across the pond? Well, we have learned that when the base angles of a right triangle or any triangle are congruent, that means that the sides are also congruent. The sides across those congruent angles are congruent. So this distance across the pond can be found by knowing the distance between points B and C. Those are the legs of that isosceles triangle. So simply measuring along the distance on the ground from B to C lets me know the distance across the pond is exactly the same thing. This is one of our special right triangles. We call that the 45-45-90 triangle for obvious reasons. That's the measures of its angles. But we have other special right triangles as well that I want us to see here. So here's that first special right triangle. We know that this leg and this leg are congruent, and so that's special. Now I'm going to pull out this vertex C, and you'll notice when I had it at the special right triangle that it got orange. And so we can see these are not special right triangles, the ones that I'm creating here. The relationship is not one that is special until I get out to make angle C 30 degrees. And now we can see, oh, there seems to be a special relationship among the sides of that triangle. I could also make angle C 60 degrees, which is the same effect. It's still a 30, 60, 90 triangle, just like when this was 30 degrees. It's a 30, 60, 90 triangle. So that is our second special right triangle. We have a 45, 45, 90, and we have a 30, 60, 90. Those are the two special right triangles that we're going to be focusing on in this section. So remember, how did the surveyor know the length of AB based on the length of BC? And that's because it was creating an isosceles right triangle. The base angles are congruent. The sides across from the base angles are congruent. So let's look at question 4 in your notes. You're going to sketch a triangle, this triangle on your paper, and you're creating a isosceles triangle because both of these angles are 45 degrees. We know these sides are both congruent. I just want you to sketch this triangle and write down the information that you know to be true, and then come back and check this video out. Okay, so some things that I hope that you recognized is that we know the three angles have to add to be 180, so these two add to 90 degrees, which leaves 90 degrees for the missing third angle. So not only is this isosceles, this is an isosceles right triangle. We know, like we said, that the legs are congruent because the base angles are congruent. We also know, since it's a right triangle, we could apply the Pythagorean Theorem to this triangle. This leg squared plus this leg squared is equal to this hypotenuse squared. And so we're going to look at what special relationship exists in this isosceles right triangle. So let's look at this second animation to help us see that. So here again, we knew this was 90 degrees because that was what was left over from the 180 degrees after the two 45 degree angles. The legs we can label as A and B, and the hypotenuse is C. And like I said, we could apply the Pythagorean Theorem since it is a right triangle. Now, since the legs are congruent, I really don't need two different variables for them. I can have them both as A. So now instead of A squared plus B squared equals C squared, I have A squared plus A squared equals C squared. Now what they're doing here is they're replacing the A's with a value. And so they're going to let these A's be 1. So you can see here they're replacing those A's with 1. And so we have 1 squared plus 1 squared equals C squared. Well, we know 1 squared is 1. So we'd have 1 plus 1, which is 2. So we would have C squared equal to 2. And we know to get C by itself, we would have to take the square root of both sides. So we would get C equal to the square root of 2. Now 2 is not a perfect square. We would not want to get a decimal approximation there. We're going to leave it in simplest radical form. So this is our first special right triangle, known as the 45, 45, 90 triangle. And this is our reference triangle, just meaning that every single 45, 45, 90 triangle is going to have the same relationship that we see here. The legs are going to be congruent to each other. So whatever this side is as the same thing. And then to find the hypotenuse, we're going to take this number and multiply it by the square root of 2. So this is the same thing as 1 square root of 2. We just don't write the 1 out in front. So like I said, this is the reference triangle. We will be using this a lot. So you'll need to go ahead and label that on your number 4. We're going to label these sides as 1 and the hypotenuse as the square root of 2. Another way that you'll see the reference triangle referred to, instead of using 1s, is using x's. And so labeling the legs as x means the hypotenuse would be x times the square root of 2. Just meaning whatever that number is, that's what's going to be in front of the square root of 2 for my hypotenuse. All right, so let's look at our first example. It says that Carlos wants to attach a stabilizing wire 5 feet high on the trunk of a new tree in his yard. And so we can see here the 5 feet high on the trunk. Here is the wire that's going to be attached to the ground. He wants to know how long is the wire. He's staking the wire 5 feet out from the base of the tree too. So he created 5 feet up the tree, 5 feet away from the tree, and that's where his wire is being attached. So we want to know how long is the wire. Well, we get to apply what we just learned, which was the 45-45-90 triangle, simply because we know these two legs are both 5 feet. So if both of those legs are 5 feet, I know both of these angles are congruent to each other. And we're assuming the tree is perpendicular to the ground. There's our 90-degree angle. Since these are both congruent and have to add to 90, that means they are each 45 degrees. So we just learned that in an isosceles right triangle, the legs are congruent, and to find the hypotenuse, we're simply going to multiply the leg times the square root of 2. Well, our leg is 5, so our C value is going to be 5 times the square root of 2. So the length of the wire is 5 square roots of 2 feet. That is our answer to number 6. Just multiply the leg times the square root of 2. All right, so let's look at question 7 in our notes, which is some more examples using the 45-45-90 triangle. So hopefully this will help you understand this a little better. So here's the 45-45-90 in both of these examples. In this example, we're given one of the legs, one of the sides making up the right angle. And in this example, we're given the hypotenuse. So make sure you understand these are the two types of problems that you'll get with the 45-45-90. Now, this answer should be super easy for you. Since these angles are congruent, these sides are congruent. So if this is 7, this is 7. Now, to remember, to get from the leg to the hypotenuse, all you're going to do is multiply by the square root of 2. So this hypotenuse is going to be 7 square roots of 2. That's it. Now, since on this one, instead, we're going from the hypotenuse to the leg, we're going to do the opposite of what we did here. So instead of multiplying by the square root of 2, we've got to divide by the square root of 2. So I've got to take 7 and divide it by the square root of 2. Now, hopefully you learned in Algebra 1 that we do not usually leave radicals in the denominator. We have to do what's called rationalize the denominator, which means get the radical out from the denominator. And so if we understand radicals well, we understand that we can get rid of that radical by simply multiplying the denominator by itself. But we know we can't just do that. If we multiply the denominator by the square root of 2, we have to multiply the numerator by the square root of 2 as well. Because now all we're really doing is multiplying by 1 and not changing the number's value. So now in the numerator we have 7 times the square root of 2. And in the denominator we have the square root of 2 times the square root of 2, which is the square root of 4, which is simply 2. We no longer have a radical in the denominator. Now I could write 7 over 2 as 3.5. But since it's a terminating decimal, but I'm going to leave it in fraction form. This is what I would consider a simplified answer. So this side is 7 square roots of 2 over 2. No radical in the denominator. Now remember, we know that since these angles are congruent, these sides are congruent. So if this is 7 square roots of 2 over 2, this side is also 7 square roots of 2 over 2. Okay, so we have to understand the legs are congruent. And then we have to know whether we're multiplying by the square root of 2 or dividing by the square root of 2. Anytime you're going from a smaller side to a larger side, you're going to be multiplying. And anytime you go from a larger side to a smaller side, you're going to be dividing. And we know the hypotenuse is the longest side of a right triangle. So that'll help us remember if we're getting bigger to multiply, if we're getting smaller to divide. Now we'll look at our second special right triangle, the 30-60-90, in the next video.